In today's discussion, we're going to start talking about the features in text data that allow us to start creating some type of matrix that we can create, let's say, a relationship between what is included inside of a text document and also how it relates to other text documents. So in this discussion, we're going to talk about feature engineering in text data. And we're going to talk at this moment what's called a bag of words model. Now, in previous discussions, I may have shared with you, if you think about the way that text is put together, we can tokenize all of the individual words. And imagine each one of those words was represented by a single marble. And we threw all of those words in a bag, or a marble, all those marbles in a bag. And we decided to start plucking each individual marble out of the bag. That would be a bag of words type model. So the whole idea about bag of words models is the idea that we're only looking at word count, and we're not necessarily looking at the relationship of those words as it relates to the document or as it relates to the corpus. So all of this will make sense as we kind of go through it. There are several other lectures related to feature engineering, but we'll put them all together and they will start to make sense. Now, I want to start with the idea that we are still following that basic text analytics process. Now, in our particular case for today's discussion, we've already established the corpus, which is going to be the text that we're going to analyze. We're going to pre-process that data, and then we're going to create a term document matrix. Now, a term document matrix is the foundational element that our feature engineering process is going to give us. So let's go ahead and get started. I've given you a start box, and it has a lot of stuff in it. And so let's just make sure that it is included. There are some things that you may have to download if they are not already downloaded into your instance of Anaconda. So let me go ahead and execute this, and I'll make sure it runs. All right, so I thought it took a little bit more time than, than I had thought. All right, so let's take a look at what this corpus is. Imagine that these 8 sentences here are each individual documents. All right, so one document is one sentence. So let's go ahead and look at what that corpus is. And each of those documents belongs to a specific category, weather, animals, food. So let's just go ahead and put labels, and let's see what I have here. We're going to display it all together so we can see all the pieces. So in a sense, this is our corpus. It's already been pre-categorized. And the reason we use this particular exercise is that if you scan over these documents, which we can do rather easily, we can see that there's a lot of similar words. There's also several stop words. And what we're really looking for are features within each document that will give us some identification that document is unique, or what is unique about that document that might relate to other documents with same features. So we're going to do some simple pre-processing. Now, this is what I call my basic normalization function. There are other normalization techniques that we could apply. I decided to use this one just for this lecture. We're going to use the word punct tokenizer. We're going to use NLTK stop words. And this right here is our entire normalization. What we do is we're going to remove special characters. We're going to make everything lowercase. We're going to strip leading and trailing spaces. We're going to tokenize each word. And then we're going to filter all the words. Filter all the stop words out, and then we're going to reassemble all the pieces. All right. We're actually going to do something really interesting here. We're going to put this into a vectorized format. So NumPy, or NP, has a vectorize function. So I will go ahead and put vectorize. And every time that we put a list of documents through this vectorizer tool, it will actually give us a vectorized set of those documents. This may not make sense quite at the moment, Actually, what I want to do is I'm just going to copy this up here. Copy, and I am going to paste that right here. Okay, so this normalized corpus is actually a vectorization tool utilizing that function normalized document. Okay, so we went ahead and executed it. Now let's apply it to our corpus. So we're going to take our vectorizer tool, which is this normalized corpus, and we're going to apply it to the corpus. And if you remember, if you remember, the corpus was that list of documents up above. Hold on a second, I'm getting ahead of myself. Here we go. So I'm basically this list right here. I am putting inside that little vectorizer tool, and then I want to display what it looks like. So now we can see after it is run through our normalizing function, we can see everything is lowercase, any kind of leading and trailing spaces or special characters has been removed, and also stop words. So look at this particular sentence number 1, if we're zero indexing, and let's go look at sentence number 1 up here. Love this blue and beautiful sky, and let's see how it is. It's just love blue, beautiful sky. All right, so that's how this normalization vectorization tool works. And if you look, everything is again in a nice list. Actually, it's a NumPy array for all intended purposes. By the way, another way that you can print this out if you really wanted to, you could go for every document in that normalized corpus, go ahead and print that document, and that might be a little bit easier to see. Or if you really want to get creative, you could just put this inside of a data frame constructor and look at it in this sense. So those are all different ways of being able to display that. So what we want to do is create this term document matrix. And let me explain what that is first, because it's easy to show you all the Python and fill in the blanks of this, but we also have to understand what it is. So here are some simple documents. I'm just going to go with 2 documents. We have Professor Plum has a green plant in his study. And we have a second document that is Miss Scarlet watered Professor Plum's green plant. So let's take all of those particular words and let's go ahead and put those in a list. Now, if you look, we only have 13 unique words that are in these 2 documents total. But words like professor, words like professor has occurred twice. If we take the apostrophe S out, we could say plum actually has appeared twice. In my list here, I have apostrophe S, so I'm actually identifying it as 2 separate words. The word green and plant also occur twice. So we can see that 13 words is actually reasonable when you look at these 2 documents as part of our full corpus. All right, so we're going to analyze each sentence, and we're going to count the total number of times that a specific term occurs in a document. And so we can see that in our first document, we have every single word and how it occurred once. We have the second document, and we have every single word and how it occurred once in this case. And on the far right, we have a matrix. We have, in column A, we have all of the terms. And in column 1, we have the binary values, 0 or 1. Actually, these are integer values. If a word occurs in the same sentence or the same document more than once, then these numbers would increase. So like if professor was in document 1 twice, we would put a 2, where currently there's a 1. And then on the column D, we can see these are the total occurrences of each word in the corpus, and we can see that professor, green, and plant each occur twice out of the entire corpus, but only once in document 1 and once in document 2. Now, let's say that we added a third document. Mr. Green has a green plant. So now, using the same process, we would add this to our term document matrix. So in column A, we would add Mr. to our term list, but all of the other words existed in the other documents. So we went ahead and just marked how many times those words occurred in that particular sentence. And we'll notice that on line, or in row 3, that we have 2 occurrences of the word green. And then now we have 4 total occurrences of the word green out of the entire corpus. By the way, if you want to do a little TDM calculations, I did put an online utility tool here for your reference, and you can always put documents inside of this tool, and you can use it to get some word count out of it. So it's helpful to double check some of your homework and also to see if things are going together. So here, this matrix, which is in columns B, C, D, and rows 3 through 16 on that little picture, that is part of our term by document matrix. So it is a term by document matrix. And really, it's just a singular count of how many times each term occurs in documents and how the total number of terms that are in the entire bag, or the bag of words, right? So here's our bag of words model. Here's how we implement this using Python. And more specifically, we're going to be using the count vectorizer tool, right? And the count vectorizer tool is from sklearn or scikit-learn. And it has a lot of information that is available through the links that I've provided. And you can go ahead and investigate those at your own preference. So here, our next block, what we're going to do is we are going to implement this count vectorizer. So sklearn feature extraction. So this is feature engineering, and this is a specific tool called the count vectorizer to assist us with that tool. So we're going to get a bag of words, and all of these blanks, I'm giving you default settings in the paragraph. So if you have any questions at any point in time, just know that I'm giving you a lot of the default stuff that's necessary in the application. So on line 5, we are going to use our count vectorizer, and with a minimum degrees of freedom of 0 and our maximum of 1. Okay, and we get this tool that's called the CV tool. So using our CV tool, we are going to fit transform our normalized corpus. Now remember, our normalized corpus is the array of the transform or normalized corpus. And then we're going to display the matrix. By the way, the matrix is going to show us the document and the token position, and then it's going to give us the... I'm sorry, I had a little error. I had to redo this. So let's go ahead and execute this. And we can see now that what is happening is we have the output, once again, document, token, position, and count. And we can see here, by looking at this part of the matrix, this is saying this particular word occurs in document 0 at position 17, and the count was once. The other one, the second word occurs in document 0, it's in position 3, and it's 1, and then so on and so forth. And we can kind of go through and see this. And if you take a look, there is a word right here that actually occurs twice in document number 6, and it's in token position 17. And if you scroll up here, and if you take a look, we can see here is document 6. Here is where that double word actually exists. So we can see that this little component right here is somewhat helpful. But what we want to do, and you have a blank here, I actually had to do some edits to our particular video. But if we take this blank here and we fill in with toArray, there we go, toArray, and execute it, we now can see all of what is up above in a matrix format. So this gives us a dense representation of all of our things. And this is actually a true term by document matrix. If you look at this, the horizontal numbers represents a singular document, and every single number indicates how many times a specific term occurs in that document. And if you think about that logic, that means the column. So if you think about the vertical number counts, like if we look at the far right-hand column, it's 0, 0, 0, 0, 0, 0, 1, 0. That means this word, this token on the far right only occurs in document, this second to last document once. But if we look at the second to last document, we'll notice that's where we have a term that exists twice. So again, we know that this third to the last column, this one right here, is probably the word sky. But we're not going to do that for all of our items, right? That's a little bit challenging to kind of guess what word exists in what particular document and how many times. But this is actually the matrix that sklearn will be able to use in order to be able to start to construct some kind of relationship of documents based on the words that are in them, and those words are features, and the rest of the corpus. So again, that's a little bit hard to read, so let's make this a little bit easier. Let's use a tool from our count vectorizer. It's called Get Feature Names Out. And we are going to show this document with the feature names. And what we're going to do is we're going to put the CV matrix that we had created up above, except this time for the columns, we are going to put our vocab that we have here from line 2. And let's go ahead and display that. And now we can see each of those words, which is now at the top. And we can now see the document number based on the index on the left-hand side. And looking again at row 6, we can see there's that 2. And as I was leading to, that actually represents the word sky. But this helps us out so that way we don't have to guess what index or what value and what other necessary items that are there. This gives us our term by document matrix with real words. So in a sense, when I talk about using a bag of words approach, I really want you to be just using this matrix here of our term by document matrix. By the way, if you paid attention, I put this little bit of code down here at the bottom, and now this also gives us the frequency count. So actually the word blue occurs 4 times, sky 4 times, and so on and so forth. So I had a question here from previous lectures. We now can identify which word appears twice in a single sentence, and I've already been leading to it by showing you that it was actually that word sky in sentence indexed number 6. All right. So what we could also do is if we want to create more features in a document, we can do something by creating n-grams. Now remember, let's take a look at what is up here in the top of the columns. Now, this is nothing more than a feature that is in a sentence, right? And this representation of integers in each row here is actually called a vector. Now, if we want to get some more qualities of the document that might help identify it as being unique, what we need to do is start to record more features. For example, if we were going to identify a human being and we just said, well, they had blue eyes and brown hair, that might be able to help us sort out some of the human beings and identify specific ones, helping us narrow down to like what human being we might be speaking of. But it might be better to add another feature, and we could think of a feature like height. So blue-eyed, brown hair, but they're 6 feet tall, right? So that's a new feature. So we do that with documents as well. We create new features to help us identify those particular documents. So I'm going to have a bag of n-gram model. So it's still a bag of words. So we're going to continue to use the count vectorizer. But this time I'm going to use BV for bag of what do I call it? A bigram. We're going to use 2 words. So a bigram is a type of n-gram, right? And we're going to go ahead and use that count vectorizer to create a new matrix. So we apply count vectorizer here. For the BV matrix, we have to fit transform it to our current normalized corpus. We're going to convert it to an array. And we're going to get the vocab, which is actually get feature names out. We're going to display it in a data frame, and we're also going to do a term by term frequency count, right? So now what we have is we have bigrams. Now, what I didn't share with you is how all of these bigrams are created, but that's okay. We can go over that real quick. So these bigrams are actually created by looking at what words actually occur together in a proper sequence. So here the word sky and blue occurs once in this document, and the word blue and beautiful occurs once in this document. Now, we don't do sky beautiful or beautiful sky. We just did those. So this first document only has two bigrams. It has sky blue and then blue beautiful. The next one would have love blue, blue beautiful, and then beautiful sky, and so on and so forth. So those are our bigrams, and now we can see how they get put together based on our bigrams. So there's our beautiful sky, there's our blue beautiful, and we can see where they occur inside specific documents. All right, and now we actually have a count. So, by the way, by adding these n-grams, do you think it can help us improve what each topic of each sentence might be? Like when we look at this, brown fox, does that allow us to give us more information about that, the documents that might include those words, and so on and so forth? Remember, we're really trying to look for unique ways of being able to identify these documents, and bigrams can add those additional features. So let's do some additional stuff. Let's kind of think about what's happening, and then we're going to start wrapping all this together into something else. All right, so something we can use, actually. So we have this text. I can't remember where I got it. I'm sure I got it from somewhere on the internet. So let's go ahead and execute this block so we can see how it gets applied. And let's do some basic sentence tokenization. So we're going to use NLTK, and we'll use sentence tokenize. And now we can see each sentence is actually now in a part of a list. And this is the kind of process, by the way, that we're going to follow. So we want to normalize that text. And what we did before, we used our normalized corpus vectorized tool. So we'll use normalized corpus. All right. And then we'll do this to my sentences, which is from up above. And let's go ahead and execute it. And now we can see that we have all of our document from up above. We have it cleaned. We have stop words removed. And each sentence is its own item in an array. All right. So let's just kind of treat each sentence as its own document. So let's go ahead and create our term frequency matrix. So we're going to now apply our count vectorizer. All right, and then we are going to do a count vectorization on this text, and we're going to create, we have to first fit transform it. We're using that tool. And if you notice that I'm going to do something a little bit different this time, instead of having another line and convert it to a matrix, I'm just going to say to array and be done with it. All right. Well, hold on, my mouse is giving me a hard time. All right, so next, after we convert it to an array, we want to get the vocabulary out. So we're going to get feature names out. And let's go ahead and apply this inside a data frame. So we're going to do my text matrix. I'm sorry, I did that wrong. There we go. And the columns is the vocab. And let's take a look at what's happening. So according to this new bit of text that we have entered into our little processing tool, this is the actual term by document or term by sentence matrix. All right. And here is the word frequency count. And what's really interesting, if you take a look at this, oh, by the way, just for reference, I did put a count of only 10 words. And that's, but if we look, we have actually 55 words in this particular document, but only a few of them actually occur twice in a sentence, which is where I was going. All right, let's do this with bigrams. Let's say that we wanted to do this type of thing using a bigram counter. We would do exactly the same thing we did before. We would do a count vectorizer. right? And let's go ahead and apply this count vectorizing tool on this n-gram range of using two words for the sentence. So this n-gram range, by the way, is the unique qualifier as to how this vectorizer actually decides on whether it's going to use unigrams, bigrams, and even trigrams. I'm going to show a couple things here in just a minute. So once again, we are going to do fit transform on our normalized text. And we're going to convert everything here to array. On the vocab, we are going to get feature names out. And we are going to, this time, use what's on line 6, which is the bivariate my text matrix. And the columns, once again, is the vocab. And now let's kind of see how this gets put together. All right, what did I do here? Oh, I typed my array with 2 R's. Okay, one more time. And now we can see actually where all the bivariates are. Why did I get my not matrix? Let me double BV my text matrix columns equals vocab. Oh, I never displayed it. That's why. So looks like I left this line of code out. There we go. And this time I want to display this. And there we go. Now we can see the execution there of the bivariate matrix and now all the words. Now we can kind of see that these really don't have any kind of strength because really they only occur once, and this has been sorted, and this is the top 10, and we can probably see that this doesn't mean anything. But let me show you something. So let's say that in an exam that I'm asking you to include bigrams and unigrams, because right now I'm just showing you how to include unigrams and then include bigrams, and these are being treated like 2 separate analyses. But truthfully, when you're looking at a human being and trying to figure out, well, how would we describe them? We wouldn't say, well, let's just look at the tall people alone. Oh, well, let's just look at the brown-haired people alone. We actually look at all 3 features, brown hair, blue eyes, and height, all at once. And the trick to that is really, for text, is going to be this line of code in our count vectorizer. The first number here represents the smallest n-gram size that we want. And notice that here I have used the number 2. But if I actually put the number 1, the smallest n-gram is going to be only a unigram. Now this second number is the largest n-gram size. And by putting the 2 here, we want the largest to be a bigram. So just by changing that one little number, and if we execute it, we're now going to see that we get both unigrams and bigrams. All right. So now we can see how all the unigrams and bigrams come together. But now let's look at what happened to our term by document matrix. It grew. We now have 112 columns, and each of those columns is a feature based on one of those documents. And this row becomes the vector that represents that document. It's kind of like a fingerprint. So now we can get some more rich features to help describe each document, and now it is all together. Now I have some questions as to what can we learn from this bag of words model, what kind of information do we retrieve, and what kind of noise do we also have. So if you haven't noticed, that what this does is that these bag of word models tend to make us look at documents and words based on how frequently they occur. But there is no weighting, W-E-I-G-H-T, there's no weighting in terms of how critical those words might be for that corpus. So for example, does the word dogs, is it in a sentence, and is it in a sentence that is of 2 or 3 words? Or is it in a sentence of maybe about 8 words? And does that have an impact on the entire analysis? So also, if the word dogs occurs frequently in the entire corpus, maybe that word dog is more important. Let's say it occurs in more documents in that corpus. But let's say that we take another word like older, and it occurs more frequently also in that corpus, but this time it only occurs maybe in 2 or 3 documents. So what I'm getting at is, let me rephrase. Let's say that the word dogs occurs in all the documents, so it occurs frequently inside of a corpus. But let's say that number ends up becoming 5 in this case, since we have 5 documents. But now let's say that the word older occurred also 5 times, but let's say it only occurred in 2 documents. And those are different situations, right? This would tell us that the word dogs actually may not help us describe anything in the corpus, but the word older, given that it might have the same count, could actually create a scenario where it might help us identify specific documents better because it occurs more frequently in those documents, right? So this bag of words approach does not give us that view. So to do that, we are actually going to do what's called a TF-IDF model, where we look at the term frequency and the inverse document frequency to identify those weighted values when a term occurs frequently in the corpus and across all documents versus when a term occurs frequently in a corpus but only in a few documents, right? So those type of things matter. So we go through a normalization process, and I'll let you look at these slowly, but these are all math calculations that we can utilize and implement in like an Excel spreadsheet so we can identify all of these components. Just to let you know, we do have some Python libraries that do all of this for us. And one of the things that sklearn does is it does an inverse document frequency that's kind of been smoothed out. So a lot of times if you look at textbooks, the IDF formula might be a little bit different. And that a lot of it has to do with smoothing. All right. And for reference, I do have a raw IDF calculation that you can use. And we can also look at what is called a Euclidean normalization, right? Which will kind of normalize things based on Euclidean distance. Now, that is a big conversation to have, probably not appropriate for this discussion today. But that is something that we can talk about when we look at distances between specific words. So as we look at TF-IDF calculation, we are now going to be able to look at the weighted values of a term, and those weighted values are going to provide us some indication as to how well we can discriminate between documents, or basically identify what those unique features are of our documents. So going back to our documents of Professor Plum has a green plant, etc., we can see that using a TF-IDF matrix, that in document 1, in his study, has the highest weighted terms that are for that document. And if we look at those words, they don't exist in other documents. So we can see that those words are the most unique features about that document. And if we had to describe a document, we could say, oh, the one that describes him in his study. And then we would know exactly which sentence or which document to look at. The second one, we can see Miss Scarlet Watered are the unique words that are different than others, and they're the highest weighted words in relationship to the other documents for the entire corpus. So we can always say, hey, find the document that talks about Miss Scarlet. And we can see that that will refer us to document number 2. Now, document number 3, the most common word is green, which happens to make it the most weighted. So we can always say, we can look for the document that talks about Mr. Green and his green plant. So that's how we use TF-IDF instead of a bag of words model. This allows us to look at the weighting between words versus the corpus, and look at ways that we can identify specific words that will help us identify a specific document. So let's continue on. Let me show you how to do this with sklearn. Now, there are 2 ways to do this. Let's say that you have already conducted a bag of words vectorization tool. Then you can use the TF-IDF transformer. It will transform a count vectorized set of matrix into a TF-IDF matrix. But let's say you have not done a bag of words vectorization. You can use the TF-IDF vectorizer. These will get you to the same destination, but it's important for me to show you how to use both of these. So the first time, let's go ahead and let's use the count vectorizer. Okay, we're gonna count vectorize or vectorize into a bag of words first, and then we're also going to then use the TF-IDF transformer. Okay, so in the count vectorization, we go ahead and we apply a count vectorizer to we create a count vectorizing object. We fit transform that object to our data. So in this case, our data is going to be the normalized corpus. And then we are going to convert that to an array. All right, so now we have this matrix here that is an array. We can now use the transformer to convert this into a TF-IDF matrix. So now we're going to do the TF-IDF transformer. Again, I'm giving you some default settings. We are going to fit transform using that transformer on this time we're going to fit transform our matrix, right? Because we want to transform the matrix from a bag of words to a TF-IDF. And then again, we're going to convert this to an array. Oh, I'm sorry, that's to array. And the vocab is going to come out of the CV matrix, so we want to get feature names out. All right, and I already have a document, a data frame to get us set up, so let's go ahead and run it. And now we can see that we have a TF-IDF matrix of each of the terms and each of the documents. And we can see here that sky, right? Remember, it occurred twice, but it is a heavily weighted term for document number 6. So we can see that the word sky is a highly descriptive word that would actually allow us to describe document 6. All right, so let's talk about now using, instead of using the TF-IDF transformer, we're going to now use the TF-IDF vectorizer, and the vectorizer allows us to skip the steps that require us to use the count vectorizer. It looks like here I've made a little bit of an error, so let's just put TF-IDF. This time it's going to be the vectorizer, and guess what? We use this like we've used our count vectorizer. We have the TF-IDF vectorizer that we implement here. Once again, we take that TF-IDF vectorizer and we fit transform to our normalized corpus, and then we convert it to an array. And let's go ahead and get those feature names out, right? And this time I'm going to apply something different. We're going to display the TV matrix. But this time, by the way, if you haven't noticed, I am rounding things to 2 decimals to make things a little simple. And then we're going to do vocab for the columns, and let's display that. So we should get the same result as up above, but this time, if you notice, less lines of code. All right. And once again, we come back and we can see that this particular word, sky, is highly descriptive. So what can we learn about our TF-IDF model? Well, what we can see is that it provides us not only a description of its features, but it also weighs them within each document to see how important they are relative to that document with respect to the entire corpus, right? And that allows us to identify key features in each document that helps us pinpoint and identify those documents. Right. So I hope that helped. There'll be more discussion in class. And of course, you can always contact me with additional questions. So let me know if you need anything. Thank you.